If you're turning wrenches or running diagnostics in a busy automotive bay, well, today is going to fundamentally change how you look at the fluid inside an automatic transmission. Our goal for this session is simple. We're going to shift your mindset away from treating ATF as just some lubricant. Instead, we want to look at it for what it truly is, a highly precision-engineered hydraulic calibration parameter that absolutely dictates shift timing.
Okay, let's dive right into this. I want you to ask yourself, how many bad transmissions have you or your shop condemned that honestly just had the wrong fluid physics? We've all seen it, right? A vehicle rolls in with a harsh shift or a flare. You pull the dipstick, the fluid is dark, and boom, the immediate thought is a mechanical hard part or solenoid failure. But as you'll see today, debunking that myth is really step one. Dark fluid does not automatically mean the transmission is mechanically dead. A lot of the time, it just means the fluid has lost its calibrated hydraulic properties.
Here's what we're covering in our diagnostic workshop today. First, how viscosity controls shift timing. Then, the physics of the shift circuit, followed by temperature and shear degradation. After that, we'll get into diagnosing shift timing symptoms, isolating TCC shutter causes, and we'll wrap up with a standard operating procedure for fluid service.
All right, let's kick things off with Section 1. Viscosity controls shift timing, which is really the hidden hydraulic parameter here.
So viscosity is fundamentally a fluid's resistance to flow, and we measure it in centistokes, or CST. Now, why does this matter to you in the bay? Because it directly controls exactly how fast hydraulic pressure builds and releases inside that transmission. Most modern ATFs fall into a super narrow range, like 6 to 8 centistokes at full operating temp. And, the trend lately has been pushing toward even thinner fluids to squeeze out better fuel economy. That means these hydraulic systems are precision-engineered to work within incredibly tight viscosity windows. Modern ATFs really rely on specific viscosity index ranges to maintain stability when those temperatures start bouncing around.
Moving on to Section 2, the physics of the shift circuit. This is all about how fluid actually moves the metal.
I want you to picture the microscopic physics happening inside the valve body during a shift. Step 1, the transmission control module commands a shift solenoid. Step 2, the ATF has to physically overcome shear resistance to move the spool valve. And step 3, that fluid flows through an orifice to fill the clutch piston cavity and apply the pack. Now, this fill time is governed by the Hagen-Poiseuille equation. Conceptually, imagine trying to push thick pancake syrup through a medical syringe. Now imagine pushing water. This syrup takes way longer, right? If your ATF is too thick, you are literally halving the flow rate. The clutch takes way too long to apply, and techs will so often misdiagnose this sluggishness as a failing shift solenoid.
Now, what's really interesting about this slide is the direct contrast in symptoms based entirely on fluid thickness. Thick ATF slows down the spool valve travel, delays that pressure transition, and you end up with these lazy, sluggish upshifts. The clutch just takes too long to fill. On the flip side, thin ATF reduces the natural damping effect in the valve body. That causes the accumulator piston to move way too fast. The result? Harsh, banging, completely abrupt shifts. This is exactly why the idea of a one-size-fits-all universal fluid is an absolute myth in modern bays. Okay, Section 3. Temperature and shear degradation. We're talking about breaking the polymer chains.
400 times. That is how much higher your ATF viscosity can be at a minus 20-degree cold start compared to when it's at full operating temperature. We're talking 1,500 to 3,000 centistokes on a cold morning, dropping all the way down to just 6 or 8 centistokes when it gets hot. I mean, this drastic swing completely shifts the hydraulic timing window. And that right there is exactly why cold start shift timing issues are so incredibly common in the shop.
Let's map out what that actually feels like in the driver's seat. In a cold fluid scenario, that high viscosity means sluggish flow. You get delayed engagements, like, that long awkward pause when shifting from park to drive, and hard shifts that eventually smooth out as the vehicle warms up. Conversely, hot or degraded fluid has critically low viscosity. This low resistance causes internal leakage, early or soft shifts, maybe a flare between gears, and slipping under a heavy load. These are situations where you might be super tempted to swap out a valve body when actually the fluid itself is just dropping completely out of the required timing window. So to prevent those wild temperature swings, manufacturers add viscosity index improvers, which are essentially long polymer chains. But here is the critical failure point: shear degradation. As fluid gets chewed up inside the transmission pump and mashed between gear teeth, those extreme mechanical stresses literally snap the polymer chains apart. Let's look at a real-world case study here. A fresh OEM ATF measures exactly 7.5 centistokes. We pulled fluid from a fleet vehicle after 30,000 miles of really severe use. The polymers were physically broken, and the fluid had permanently dropped to 5.8 centistokes. That permanent viscosity loss ruined the hydraulic pressure stability and completely altered the shift timing calibration. Let's transition over to Section 4, Diagnosing Shift Timing Symptoms. We've got a really handy diagnostic matrix for you. And this brilliantly illustrates what you should be looking for. Try using this matrix on your next test drive. If the shift is soft or slow, the root cause is likely high viscosity. If it's harsh or banging, you're looking at low viscosity or shear degraded fluid. But what if it's delayed and then suddenly slams in harshly? Well, that's extremely high viscosity causing a fill time overshoot. And if the vehicle drives perfectly fine when it's warm but has problems when it's cold, you are definitely dealing with a sheared VI improver package. You are literally feeling the fluid dynamics right there in the seat of your pants. But, how do you actually distinguish between real mechanical valve body wear and these invisible viscosity-related timing errors? You've got to look at the electronics. A transmission running shear degraded fluid will very often show adaptive shift data that's been pushed to its absolute limits. Why? Because the TCM is desperately trying to compensate for that super thin fluid. You'll also likely see an increase in P0700 series codes, which indicate out-of-range pressure sensor data. And crucially, the fluid might look and even smell perfectly fine, but when you put it on a viscosity meter, it fails the spec completely. Moving into Section 5, Isolating TCC shutter causes. Are we dealing with fluid or friction? Okay, here's another incredibly common scenario. A customer comes in complaining of a vibration at light throttle during lockup. Far too many techs will immediately condemn the torque converter. But guys, TCC shutter is almost always a fluid physics problem. The shutter happens because the ATF is too thin, which provides totally inadequate film strength. Or the ATF is oxidized, meaning the friction modifiers are degraded. Or honestly, someone just put in the wrong ATF specification entirely, which gave the clutch the wrong friction modifier package and is causing it to grab and slip inconsistently. You must always verify the fluid condition before you even think about replacing that converter. And that brings us to Section 6, our fluid service standard operating procedure, so you can actually verify the fix. First off, let's quickly establish the baseline service intervals. For normal driving, we're typically looking at 60,000 to 100,000 miles. But for severe duty, like towing or heavy fleet use, that gets slashed down to 15,000 to 30,000 miles. And if the unit ever overheats, that requires an immediate fluid and filter service, no questions asked. Remember what we said earlier, clear, bright red fluid can actually be severely shear degraded, and really dark fluid might still have perfectly fine viscosity. Color is absolutely not a substitute for proper specification testing. So the crucial point is this 3-step SOP to verify your fix in the bay. Step 1, field test the fluid. Grab a portable viscometer or use a lab test to confirm the viscosity is within 10% of the new fluid spec. Step 2, flush the system with the exact correct OEM spec ATF. Please do not use universal fluids here. And Step 3, perform a TCM adaptive reset using your scan tool. Remember, if that transmission has been running on thin, degraded fluid for 30,000 miles, the TCM has adjusted its adaptive limits to match that bad fluid. If you just dump fresh, thick fluid in there without resetting the TCM, it is going to shift incredibly harshly, and that customer will be right back in your bay complaining. I want to leave you with this provocative quote directly from the technical guides. Using the correct ATF specification is not a recommendation. It is a hydraulic system requirement. Every single solenoid plus with an adaptive shift table is calibrated to a highly specific viscosity curve. So the next time a slipping or harsh shifting transmission rolls into your bay, before you go condemning the solenoids or the hard parts, ask yourself, is the transmission actually failing, or has the fluid simply forgotten how to push the metal? If you aren't testing fluid viscosity in your shop today, how much revenue are you throwing away on misdiagnosed hardware?